This conference has received generous support from the National Science Foundation. Also, we would like to acknowledge and thank the support of Peter Constantine and the program in Applied and Computational Mathematics here at Princeton as well for both financial and organizational support. And I'd just like to say that in addition to having eminent speakers, we also wanted to make sure that we represented the fact that science continues, and that not saying that our next speaker is not eminent, but I will say that he is that he is. I will acknowledge that he is young, and that this was an intentional. We wanted to make sure that we included have a youth movement in the conference, and show the various generations of science that are working on such problems. So, our next speaker is Braxton Osting from the University of Utah.
Yeah, so thank you for the very warm welcome. I would like to thank the organizers for organizing this and for inviting me. It's whoa. I was a student of Michael Weinstein's at Columbia. I finished in 2011. And just before I begin, I'll just say Michael was an outstanding advisor. Of course, everyone knows, he's interested in very interesting problems and is very generous with his time and ideas. And so I'd like to thank him and wish him a happy birthday. So the work I'm going to talk about today, I started after leaving grad school as a postdoc at UCLA, and this is work on graph partitioning. But I think he'll agree that many of the ideas I'm going to have to talk about today actually come from the work with him in our studies of scattering resonances. And so he'll see this appear in the talk. And I'll just say that graph partitioning in general comes from the computer science. And so our approach to this problem is different than most approaches. So I would say that our approach is more geometric and PDE and spectral theory driven. And so if you're not familiar with this problem, the idea is that you just want to identify meaningful groups or clusters within a data set. And by data, I'm going to take this to mean a symmetric similarity matrix. So entry ij of this matrix W represents the similarity between entries I, or items I and j in your data set. And so actually constructing this matrix itself is a problem, but so I'm going to take this as the starting point. This is the data. And of course, you can equivalently view this as a problem on a graph by assigning each item a vertex, and then you can view this matrix as a function on the edges. Okay, and so there's many applications for graph partitioning. Clustering and machine learning is the dominant one. For example, document classification or community detection in social networks, but also image segmentation and domain decomposition for scientific computing can also be viewed as this problem. And the challenges for this problem is that you have large high-dimensional data sets, and that typical formulations of the problem lead to NP-hard problems. And then there's another point that I'd like to make is that the measure for optimality for a partition is it can be application dependent. And so I'm gonna talk about a criteria that's not usually used, and I'm not claiming necessarily that it's better than the old ones, but for some applications it might be a relevant one to use. Okay, and so I'm going to talk about two methods really for graph partitioning. The first one is referred to as the Chigo partition, and then I'm going to introduce this new one that's called we call the Dirichlet partition. And so I'll first talk about the Chigo partition, and this is one that's more standardly used, and then I'm going to talk about many properties of the method for solving the Dirichlet partition problem. Okay, and so just to start out, let me just introduce some notation. I just want to bipartition this graph, and the naturalist starting point is to define the perimeter of a vertex subset. So if I have a subset of my vertices S, then the perimeter is just, well, it's the number of vertices, or the number of edges that connect the vertices in S with the vertices in the complement of S. Or if you have a weighted graph like we have, it's the sum of the weights on those edges that connect S to S complement. And then if you want to partition the vertex set into two pieces, well, the first thing you might think to do would be to minimize this perimeter between the S and S complement, but this will give you a trivial partition. And so what people do is they introduce this Cheeger cut or the balanced cut criteria, where you divide the perimeter of the set S by the minimum of, this is the volume of S and S complement. So if either S or S complement is small, this denominator is a small number, and so that would be a bad partition, so you minimize overall partitions. And so you roughly obtain a partition where S and S complement are the same size, and the perimeter between them is small. Okay, and so this is an NP-hard problem, so that's one challenge, and then the other one is it's not immediately clear how to extend this to a higher number of partitions, but I'll address that in a second. Okay, so let me just say a few ways about how you might minimize this quantity. So the first idea is to do something called spectral clustering, and this is an idea of Shi and Malik, and you start by introducing the graph Laplacian. So I told you what W is. This is the similarity matrix. And then from W, I construct the degree matrix. This is a diagonal matrix where on the diagonal are the row sums of W. And the reason why you introduce this graph Laplacian is it has very nice spectral properties. Namely, the first eigenvalue is 0, and the second eigenvalue, well, of course, it's characterized by the Rayleigh quotient. And this is called the Fiedler value of the graph, or sometimes the algebraic connectivity. And one nice property about this eigenvalue is it's bounded above by twice the Cheeger constant, and below by the Cheeger constant squared over 2. And the idea of Shi and Malik was to use the eigenvector associated with this eigenvalue. They take a superlevel set of that eigenvalue. So they choose gamma. Maybe you might try to find the optimal gamma, or maybe you choose gamma equal to 0. And then they take this set of vertices, and then S and the complement of S, this bipartitions your graph. And so the nice thing about this is it's very simple and fast. And in many cases, it's a good approximation of the Cheeger cut, but you can construct graphs for which it's not. Okay, and then kind of the second idea for finding the Cheeger cut or approximating the Cheeger cut of a graph is to use the total variation. So the graph total variation is defined like this. This is almost like the Dirichlet energy of the graph, except there's just a power of 1 here. And one nice property of the total variation is that if you compute the total variation of a function that's the indicator function of a vertex subset S, that ends up just being the perimeter of S. And what Schlamm and Bresson were able to show is that if you consider this minimization problem, so this is the total variation of a test function f divided by, this is the L1 norm of f minus the median value of f. So this is a somewhat strange quantity, but if you minimize this over all vertex functions f, you call that lambda. Lambda is exactly the Cheeger constant for the graph. And if you take a minimizer and you take a gamma superlevel set, that will be that will give you the Cheeger cut. Okay, and so this is just kind of illustrating where the spectral relaxation fails and where the total variation relaxation is tight. Yes.
Is W skew symmetric? Do you change sign when you go backwards?
We always take it to be similarity. So if I is just as similar to J is to I. Yeah, that's right.
So you mentioned that Cheeger cut is NP hard, but then you relax it to this guy. So where is the NP hardness?
Oh, this is a hard functional to minimize. Yeah.
So still NP hard.
Still NP hard. Yeah. Okay, so that's kind of the functionals for the bipartition case, and this is how you extend it to the multi-class partition case. And so this is, maybe you might expect, you kind of sum over the partition components of a quantity that's just the Cheeger constant for each, or the Cheeger ratio for each, the balanced cut ratio for each partition component. And this also has a relaxation that you might anticipate from the bipartition case. Okay, and so now there's many methods for minimizing total variation on a graph, and you'll notice from just these methods, these are the continuous analogs of these methods are very much related to mean curvature flow in the continuum. And so this is one problem that we're interested in trying to formalize. What does it mean to have the curvature of a vertex subset of a graph? And is there mean curvature flow on a graph if your graph is not embedded? If your graph is embedded, maybe you could use many ideas about, from the continuum to try to define what mean curvature flow is. But if you just have a graph, maybe it's not so clear. And so this is a problem I worked on with Yves van Gennep, Nestor Guillen, and Andrea Bertozzi. And our approach was to think about the variational characterization of total variation. So these kind of ideas carry over to the graph setting very naturally. And you might know that the total variation also, I introduced it using this definition, but it also has a variational characterization. As the maximum, on the graph, it's phrased as the maximum overall edge functions of this quantity. And so if you want to define the curvature of the boundary of a vertex subset, in the continuum, you know that this function is maximized by the normal vector field. And so it makes sense on the graph to define the edge function that maximizes this quantity as a normal vector field. So this is a function on the edges. And then in the continuum, of course, if you take the divergence of the normal vector field, you get the curvature of the set. And so we can do the same thing on the graph. You have a graph divergent that's just the adjoint of the graph gradient. And so that's what we define as the curvature of a vertex set. And one thing that's interesting that comes out of this is that this is different than if your graph comes from a discretization of the continuum. The quantity that we get by doing this is different than if you were to simply discretize the continuum curvature. And so
what's R?
Oh, what is R? R is a parameter that we introduced to interpolate between two of the standard graph Laplacians. So you probably would recognize this if you said R equals 0 or 1. That would be your favorite graph Laplacian. Yeah. It's simply a way of weighting. Mm-hmm. Okay, and so that's how we define the curvature of a vertex subset. And then we can also introduce a mean curvature flow on a graph by looking at this problem here. So we can consider at each time step, so it's a discrete time flow, and at each time step we're going to find the vertex subset that minimizes this quantity. And so maybe the details here aren't that important, but this is roughly just the change in perimeter of this vertex subset plus the distance to the previous solution. And what we can show is that this quantity can also be relaxed. We can instead consider the minimizer of this convex functional. So this is very much like the result of Schlamm and Bresson. And if you find a minimizer of this convex functional, then any superlevel set will also be a minimizer. And so this does define a sequence of vertex subsets. Okay, and so this is the takeaway message I want you to have for this part of the talk is that methods for minimizing the shear cut and for finding optimal partitions for this, they're morally equivalent to evolving a vertex set by mean curvature. Maybe I'll just pause for a second because this is an expression. If you've ever worked with Michael, he has several of these kinds of expressions that are very beautiful. And so this morally equivalent to is something that I've adopted in my own language, and this is due to him. Okay, so maybe I'll also just briefly say on a graph, both of these problems of Schlamm and Bresson, or these flows or optimization problem that Bresson and Schlamm introduced, and then our mean curvature flow, they both involve minimizing total variation. And I just want to say that if you want to do this on a graph, you can use a lot of the ideas that come from the continuum, namely these diffuse interface methods and also diffusion-generated motion. These can also be extended to the graph setting, and these are very efficient methods on a graph. Okay, so now I'd like to get to the second graph partitioning method, and this is the one that's based on eigenvalues of graph subsets. And this is also inspired from a continuum problem. So maybe you're familiar with this problem. If I have, say, a bounded open set, subset of R2, then I can consider the partition obtained by minimizing the following quantity. So on each partition component, I'm going to look at the first Laplace-Dirichlet eigenvalue. Okay, and then I'm just going to sum over all of the partition components. So this is the sum of the first eigenvalue for each partition component, and then I'm going to minimize over all partitions. Okay, and so this is these eigenvalues. This is the first eigenvalue of the Laplacian with Dirichlet boundary conditions. And if you look at some simple domains, so I mean, I can consider the sphere and try to partition this into three components. And as you might expect, you get this Y partition as the optimal one. And then also, if I look at this is a torus, so there's periodic boundary conditions here. And if I minimize this quantity for an integer squared number of partitions, I get this nice honeycomb structure coming out. And so in the continuum, there's been many papers studying the existence and regularity, symmetry, and asymptotic behavior as the number of partitions goes to infinity for this problem. And so this is a problem we want to look at on a graph. And maybe I'll just say a few words about why you might consider the eigenvalues of the partition components. And I want to argue that the first Dirichlet-Laplacian eigenvalue is very similar to the perimeter in a few ways. One is that they both have isoperimetric inequalities. So, of course, the perimeter squared of a domain over the volume, this is always greater than that value for the ball. And there's an analogous inequality for the volume times the first Laplace-Dirichlet eigenvalue. That's always bounded below by the quantity evaluate the ball. In other words, if I minimize over all domains of this quantity, I'm going to obtain the ball. And so this is an inequality is due to Faber and Cron. There's also very nice honeycomb conjectures for both of these partitioning problems. Well, the first one is a theorem now. So this theorem says that the honeycomb is the partition of a torus into regions of equal area with the least perimeter. So this was proven by Hales in 2001. And it was conjectured in 2007 by Caffarelli and Lin that the honeycomb is also the partition of a torus into regions which minimize the sum of the Dirichlet energy. So the honeycomb is also the optimal Dirichlet partition. So here's some computational evidence of this conjecture. So here's a large number of partitions, a partition with a large number of components that ends up being very nearly hexagon, except well, they use Dirichlet boundary conditions, and so it's not quite hexagonal around the boundary. These are the associated ground states to each of these partition components. So it's the eigenfunction on each partition component. Okay, and so you can ask what happens if you kind of phrase the same criteria on a graph to partition the graph. And so this is work with Chris White and Edward O'Day. And we looked at, so just to remind you, we're going to work on a graph with weights, and we're going to partition the vertex subset into k components. And to do this, we're going to talk about the Dirichlet energy of a vertex subset. And this is simply finding the minimum of the Dirichlet energy, subject to the eigenfunction has to be 0 on the complement of the vertex subset that you're interested in. And so again, I have here I've actually introduced the notation R. This is just an interpolation between two of your favorite graph Laplacians. Yeah. Okay, and so and then to consider the energy of a K partition, I'm going to sum over the partition components of these energies. Okay, and so the graph partitioning problem then is to find the partition that has the smallest energy, and so this is very similar to the Cheeger partition problem, replacing this quantity by the first Laplace-Dirichlet eigenvalue. And as stated here, this graph partitioning problem feels very combinatorial. I don't know how to approach this directly, so I need to find some kind of relaxation of it. And so this slide explains this one relaxation of this problem. So this is the new functional I'm going to introduce, and so let me explain all of the pieces in this functional. So I'm going to relax the eigenvalues. I have some relaxed eigenvalues, and instead of minimizing over partitions, I'm going to minimize over families of k functions. So let me explain what this is. So instead of considering the Dirichlet eigenvalue on each partition component, I'm going to consider a function that takes values between 0 and 1. And for this function, I'm going to look at the eigenvalue of this entity. So I no longer have a Dirichlet boundary condition here. Instead, I have, well, this is really the potential for a Schrodinger operator. So 1 minus phi is going to be the potential. And so in particular, the important function here is when phi is the characteristic function for a vertex subset. And so 1 minus phi is the characteristic function for the complement of that subset. And so this is like a potential well centered at the set S in that case. So this is maybe a natural thing to consider, and you might expect that as alpha goes to infinity, these relaxed eigenvalues, these converge to the Dirichlet eigenvalues. So that's something you can show. And now instead of considering partitions, we're going to consider families of k functions, and these k functions are going to take values between 0 and 1, just like this. And at each vertex, they sum to 1. And in particular, if you're given a partition, if you take the characteristic functions for those for the partitions, then that will be an element of this admissible set. Those are the important elements of this admissible set. Okay, and so now, given then a family of functions, I'm going to define the relaxed energy for this family of functions as the sum of these relaxed eigenvalues. And so now I think I've explained all of the components of this relaxed problem. Okay, and so the point of doing all of this is that if you minimize this relaxed objective, what you can show is that well, the minimum is non-negative, and every local minimizer is a collection of indicator functions. And so those indicator functions, they define a partition. So by solving this problem, you get a partition, and at least intuition is that as alpha goes to infinity, you're approximating the partition from the original problem. Okay, so now I want to explain an algorithm for minimizing this relaxed problem, and we call this a rearrangement algorithm, and it's inspired by algorithms that come from other eigenvalue optimization problems. And the idea is that I'm going to rearrange these potentials at each step according to the eigenfunction. And so what I do is I start with an initial family of functions phi, and then I compute the eigenvalues for each of these functions phi. So eigenvalues and the corresponding eigenfunctions. So psi I here, these are the first eigenfunction for the ground state of some Schrodinger operators where the potential is each of these phi I. Okay, and now, so I have k different first eigenfunctions for k different potentials. And now I'm going to, for each node, I'm going to do the following. So let me think about just one node for a second. At that node, I have k different eigenfunctions. And I'm going to choose the eigenfunction that's the largest for that node and assign the label from that eigenfunction to that node. Okay, and now I can do this for each of the nodes in my graph. And so now each node has a label assigned to it. And then I can take the indicator functions for those labels. So, and then I repeat. So that's my new family of functions for this algorithm. And so just to kind of reiterate, I compute k different eigenvalues, each associated with a different potential. I do this rearrangement by choosing the eigenfunction at each node that's the largest, and then I take the indicator for those labels, indicator functions for those labels, and repeat. So it's a very simple algorithm, and what we can prove about it is that every non-stationary iteration results in a strict decrease of this relaxed objective, and as a consequence, the algorithm terminates in a finite number of steps to a local minimum. And okay, and so in practice, the number of steps is very small. So I have a couple of numerical experiments to kind of demonstrate this. So this is the first one is the very simplest one you can imagine. I'm just going to take two Gaussians in the plane and sample both of them, and then I'm going to construct a graph according to this. People call this a Gaussian kernel. So I just construct weights for my graph according to this function, and then so I run this rearrangement algorithm. I construct the graph Laplacian. I run this rearrangement algorithm, and I get a partition that agrees. Well, I get a good partition. So this is a very easy example. So any partitioning algorithm will give you this kind of partition. I guess I want to emphasize, though, that you have some additional information with this partitioning algorithm. You have these eigenfunctions associated with each domain, and those contain additional information. And so I want to interpret the values of these eigenfunctions as the confidence that, so the value of an eigenfunction at a vertex will be the confidence that that vertex is a member of that partition. And so in particular, you can take the vertex for which the associated eigenfunction is largest, and that should be the partition representative. And so that's an important idea in document summary and this kind of machine learning. So you want to have representatives from each partition. This also gives you an additional thing. If, like in this example, your data comes from a feature space, then you can interpolate the eigenfunctions to this feature space, and that gives you a way to classify new points in your data. So by solving this unsupervised problem, you now have a supervised learning method as well. Okay, so this example is very similar to the previous one. It's just more points, and now there's five different classes. So this is an example for which the simplest kind of partitioning methods will fail. And so this is a good sign. I want to just emphasize that this partition was obtained from a random initial configuration in just 10 iterations. So it's a very fast converging method.
So in this kind of, do you let the algorithm know that there should be 5 regions?
Yeah, we do. So the question was, do we tell the algorithm that there should be 5 regions? And so this is information we give the algorithm. Mm-hmm. But that's not so different than if you were to use the Cheeger partition algorithm, you would do the same thing. There are algorithms that don't require this information, but they rely maybe on a smart choice of some parameters or something. So, mm-hmm.
Couldn't your algorithm actually decrease the number of partitions from one step to the next?
That could happen as well. Yeah, it could be.
Guarantee that you keep the number you want.
The question was, is it possible for the algorithm to decrease the number of partitions from one iteration to the next? And this is also possible. So one way of choosing the right number of partitions would be to just start with a large number and let it drop partitions if needed. I don't know of a way to guarantee that the number of partitions stays the same. Well, that's not true. You could also require that so if you have some information in the beginning where you know that some vertices are a part of some partitions, you can at each iteration fix those ones, and then you'll keep the same number of partitions. So this is sometimes called a semi-supervised learning method in this kind of community. Okay, so the next numerical experiment, so this is experiment on real data. So here we have 70,000 handwritten digits. This is called the MNIST handwritten digit set. And for this algorithm, we achieve state-of-the-art, a purity of 96%, which is comparable to state-of-the-art algorithms. And so this is called this is the confusion matrix. So this says that our largest mistake is we confuse some 8s for 6s. That's how you should read this. And here I have the digits that are the representatives from each cluster. So I guess this is the 3 that most looks like a 3 out of this data set, according to our algorithm. And these are the cluster means. And so you can see that each cluster is pretty pure just by looking at the mean. So this is a slide that maybe I'll skip in the interest of time, the details, but this is just to show that there is a difference between what we're doing and the spectral clustering of Shi and Malik, even for the bipartitioning case. Algorithmically, they look at the first k eigenvalues and eigenfunctions for a single operator, and we're looking at the first or the very first eigenvalue for k different Schrodinger operators. So that's the main difference. There is a connection to what we're doing with what's called non-negative matrix factorization, and so let me explain this. First, what this is and how it's used for graph partitioning. So generally, a non-negative matrix factorization is when you try to factor a matrix A into H transpose, and you require that the entries of H be non-negative. And for the graph partitioning problem, you usually additionally assume that the columns of H are orthonormal. And these two constraints together, these imply that the columns of H have disjoint support, and it's the supports of these columns that indicate the cluster labels. And this method for graph partitioning is also known to achieve state-of-the-art purity values. But at least in my view, the algorithms used to minimize this quantity, they're very complicated and they're heuristic and they're not very interpretable. And so you'll notice that the references I have here are mostly from the machine learning and the computer science literature. And so we can show that for one value of R, so for one of the graph Laplacians, what we're doing is the same as the non-negative matrix factorization problem. So for this graph Laplacian, so that's another thing I didn't say is that for non-negative matrix factorization in general, it's not clear how you choose this matrix that you're going to factorize. There's many different choices for it. It somehow represents the data. So if you were to choose this matrix to factorize and solve the non-negative matrix factorization problem, that's the solution is exactly given by these eigen, d to the minus 1/2 times the matrix where the columns are the eigenfunctions for this particular choice of graph Laplacian. So this equivalence gives a geometric interpretation of the non-negative matrix factorization approach, or a geometric algorithm for finding this matrix factorization. Okay, I also want to say that this problem is related to a very interesting random process, and this is something that we want to learn more about and we're trying to study. So this random process, it's a random process from many particles, and each of the particles has a color, and there's k different colors in total. And these particles each have their own Brownian motion, and they obey some rules. So if two particles of different colors meet, they're both annihilated. And if any particle runs into the boundary of the domain, it's annihilated. And every time a particle is annihilated, what you do is you find another particle of the same color somewhere in the domain, and you just duplicate that particle where it is, and then they follow their own Brownian motion again. Okay, and so with these rules, you can see that the total number of particles of each color is conserved. You have a question?
I'm sorry. Just when you place this other particle like random in the domain,
Mm-hmm.
what if that site is already occupied?
So the question is, what happens? So when you duplicate a particle in the domain somewhere else, what happens if the particle, if that spot is already occupied? Well, you mean by a color of a particle of a different color?
Either the same or different.
Yeah, it's okay if they're the same, and I guess it never happens that you land exactly at that place with a particle of a different color. You have to be a little bit careful about how you phrase this, about what it means for two particles to actually meet. So it's some limiting process where they come within some distance of one another. Okay, so yes, Gideon?
Is that important to be able to have the annihilation when they get within some epsilon distance to the dynamics?
Yes, so the question was, is it important for the dynamics if the two particles to have this annihilation?
Well, not the annihilation itself, but the annihilation due to particle-particle interaction as opposed to killing at the boundary.
Yeah, so I mean, the consequence of this particle-particle interaction is that particles of different colors can't live in the same place, right? So what happens is by duplicating these particles always at the location where there's already a particle of that color, what ends up happening is that particles of the same color can kind of live in the same space, and they can't live in the spaces of the particles of a different color. And so what happens is that the equilibrium solution or state for this random process is that the colors kind of find their own place in the domain, and you can see that the Laplacian is going to give this Brownian motion, and the Dirichlet boundary condition is the same thing as these particles of different colors not being able to be in the same place within the domain. And so here's some pictures with the stationary states of this process with different number of particle colors. And so this is, in physics, this is referred to as Renyi entropy production. And so even in the continuum, the connection between this random process and these Dirichlet partitions hasn't been sorted out yet. There's many conjectures. It's conjectured that the stationary states of this process are exactly the Dirichlet partitions, but proving that is, as far as I know, hasn't been done. And also there's some problems with kind of framing the graph problem of this random process. But there is an energy associated with this process, and you can do things like, you can study this energy. Do you have a question?
Just curious, have people tried to use this as a particle method with partitioning? I mean, you initiate random walkers and has them with the color everything.
Yeah, and so this is something we're very interested in. The methods that come from this process, they're very much like PageRank. They're very fast. They're faster than the method that I just explained with this relaxation, but we can't prove anything about them yet. And so this is still something that we're working on. We're very interested in. You can think about this as the eigenfunctions corresponding to each of the random walkers are more or less the PageRank associated with each partition component. You can think about it like that. Mm-hmm.
Do the colors continue to evolve?
Do the colors continue to evolve?
You've got, I presume that these are sort of near equilibrium textures.
Mm-hmm.
As you continue to run the process, do you see exchanges?
Well, if you have a lot of particles, you won't see exchanges. Yeah, that's right. So once each color particle kind of has its own space, that will stay there. Yeah. Okay, so one question now that's natural is what are the differences between the partitions you obtain from the Dirichlet energy and these ones you obtain from the Cheeger constants? And one idea we had to address this this is, and this is work with Dominique Zoso, was to introduce a functional that kind of interpolates between the total variation and the Dirichlet energy. And we thought that by introducing this functional, we could maybe answer some of these questions. And so this is also still ongoing work. You can see that for this energy, and this energy is sometimes called the Beltrami energy, it's the energy that arises in the study of minimal surfaces, that if you take the limit as beta goes to 0, you recover, well, the volume plus a Dirichlet energy, and if you take the limit as beta goes to infinity, you get back the total variation. And so this has been used a lot in image analysis as kind of a regularization of the total variation, but we're interested in this quantity for all values of beta. And one thing that comes out of looking at this function is that you get an interpolation also between the isoperimetric and the Faber-Cron inequality. So this is an interesting result. And so maybe if I can just motivate for a second, looking at this functional for the partitioning problem. Like I said, this functional is it arises in the study of minimal surfaces, and in particular in Plateau's problem, where you try to find the surface with prescribed boundary conditions that has minimal surface area. And so here, I guess this is one way of phrasing the problem where U is equal to F on the boundary, or nearly F, and then has minimal surface. And so you could also think about kind of physically what's happening here is that you've stretched an elastic membrane over a wire that values F. And now you can also think about kind of blowing from beneath this wire until this elastic membrane has volume V. And so that would be physically the solution to this problem would be the shape of a bubble with volume V. And then if I call this value S of omega and V, then I can maybe consider the sum of all these values S for each partition component in a partition. So I want to think about this as kind of the foam that would result if I minimize each of the surface areas, the sum of the surface areas for each partition component. So I was just in ICIAM, and so this is a picture taken from what's called the water cube there, and this is inspired by these kind of foams. So maybe I just say that one motivation for studying this kind of foam formulation of the partitioning problem is that foams are very, very beautiful. Okay, so I'll just say that this is ongoing work, and one of the real challenges for actually finding partitions for this problem was the inner problem. So actually defining the minimizer for just for this minimal surface functional for one partition component, and then you have to minimize over all partitions again. And to solve the inner problem, we spent quite a bit of work on looking at this problem, and we found that an efficient way to do this was using primal dual methods. And so these are methods that were developed by Chambol and Pak. And the idea is that you rewrite the minimization problem in this saddle point formulation, and then you alternatively minimize the primal problem and then maximize the dual problem. And so this is this is the method that we use for finding just the minimal surface for each partition component, and then for the outer problem, for the problem of finding the optimal partition itself, we can use the same rearrangement algorithm as before, where instead of using the eigenfunctions, we just use the ground state of this energy. Okay, and so I'll show you some results. These results, so we see the same partitions come out for other values of this interpolation between the Cheeger and the Dirichlet case. And so we find this very interesting, the honeycomb. It looks like the honeycomb lattice is not just the minimizer for the perimeter and for the Dirichlet energy, but it looks like maybe a much larger class of energies. It's the minimizer for We also look at, this is results from partitioning 3 space. So again, this is with periodic boundary conditions. And the green, these are the interface between the 2 partitions. And then the colors here, the red, the white, this is just one of the ground state energies. And so here you have kind of a slab partition that's repeated. So this is a local minimizer for this problem. The best partition we found is very similar to this Schwartz piece surface, which isn't surprising because this is a minimal surface, minimal area surface, and so even for the Dirichlet energy, it looks like this is also the optimal partition. Okay, and so we also looked at many other domains. So here are some examples from Barbell and Annulus. Maybe I won't dwell too much on this. One thing that's interesting is, again, even for this other energy, this is something that happens for the minimal surface problem. Or if you have a partition that wants to come together and have 4 different partitions meeting at a single point, you always have that's not optimal. You always have 2 3-way junctions right next to each other. And so this also happens for these other energies too. So we find this very interesting. Okay, and so finally, this is my last example, is you can look at a variety of image segmentation problems. So here's a picture with some cows and a sky and grass. And so we can partition this using this algorithm. And so one of the challenges here, of course, is actually just constructing the graph. And my collaborator, Dominic, is kind of an expert at this. So we can also partition some other segmentation. So here's a much more challenging problem. This is a zebra, and you can imagine, kind of a very naive algorithm would get stuck on one of the stripes or something. And so you can also you can construct graphs using these kind of similarity measures between pictures based on the Wasserstein metric that can also segment images that have some kind of texture associated with them. So maybe I'll just conclude by saying that I think about all these kind of graph partitioning methods as geometric methods for graph partitioning, as opposed to more computer science ideas. And there's many open questions relating these different notions for mean curvature flow-on graphs, and also very interesting and fast computational methods that can be developed for the optimal spectral partitioning. So yeah, thank you. If you have any questions, I'm happy to take them.
Questions? Yes, Jeremy.
So you mentioned that you can prove that you converge to a local minimum, but when you're generally doing your simulations, how many local minimum do you find, and how many ensemble sort of calculations do you have to do to observe the appearance of what looks to be the global minimum?
I mean, so the question, I guess I don't have to repeat because you have the microphone. It depends a lot on the graph, of course. I mean, how many local minimum. If your data is good, you generally won't have very many local minima. I guess that defines what good means. But the hardest problems are actually these continuum problems where you discretize the continuum. There's not a lot of structure, or the structure is very global. And it's not obvious what the best partition is. And so to answer your question, practically what we do when we try to partition data is to just start with many initial conditions, maybe 10 different random initial partitions, and then we take the best objective value. So that's what I've reported here. Just one more thing is that there's a couple of data sets for which there's ground truth information, so you know the classes. And so one interesting thing to do then, when you have different objective functions is to compare the purity value for each of these the clusters between the different methods, and so it sometimes is the case that often is the case is that the partition that you find has a lower energy than the ground truth partition, and so that indicates that maybe that your criteria for selecting the optimal partition doesn't agree with the data, and so maybe that's a modeling problem.
Could you comment on how you make a graph out of an image, say zebra? So what's happening, just generically? So how do you assign nodes and the weights and all that?
So the easiest way to do this, so there's two different constructions here. This construction just compares the value. So at each pixel you have different colors associated, right? And so you can compare the intensity of each of those colors for each pixel. And so usually what you do is you don't compare all different pairs of pixels. You randomly select a subset of them, and so you have a sparse graph. And so that's typically what's done. Another way to do this is for each pixel, you find the best. You look at the histogram of the colors associated with those pixels, and then you find the best transport map and use that value. So you try to rearrange one histogram to the other, and you compare the pixels that way. So this is kind of you would call this a patched-based similarity metric.
This is also a time-consuming problem.
This is also a time-consuming problem. One thing that people do is as I said, they don't compare every pair of pixels. They only take a random subset of them.
All right, then let's thank the morning speakers.